An object is placed near a convex mirror, as shown in this diagram, and you want to draw a ray diagram for the object. So the rays are the same rays that you draw for the concave mirrors. So we're going to start with the P ray that goes from the top of the object parallel to the axis until it hits the mirror. When it hits the mirror, it reflects along a line containing the F. Well, since the F is on the behind the mirror now, the ray cannot hit the mirror and just jump into it, so the ray has to reflect away from the F because it's on a line containing the F. So take your ruler, line it up like this, and draw the ray going outward away from the F like that. We can draw the F ray. Remember, that's the one that starts where the top of the object is and goes toward the F, which in this case it would go like this, but obviously it can't go into the mirror, so it goes toward the F. So we'll draw it like that. But once it hits the mirror, it has to reflect, and it reflects parallel to the axis. So this one goes that way. So you can see that these two rays are diverging away from each other, which means that we're going to have to backtrace them to the other side to form the image. Let's go ahead and draw one more ray, and I'm going to draw the M ray. That's the one that goes toward the midpoint of the mirror, right there, and reflects at the same angle. So it's this one. And then if we trace all of these backwards, just the reflected parts, for the purple one, which was the P ray, tracing that backward, looks like that. For the red one, tracing it backward, that's the parallel part is going to be traced backward, looks like that. And for the blue one, tracing the reflected part backward, looks like that. And you can see that all three of these rays join roughly in that same spot right there, so I can put the final image as a little arrow that goes up to that point where they all cross. So based on this, because the image is on the other side of the mirror, it is virtual. Since the arrow is pointing upward, we can say it's upright, and then we can see in this case that the image is smaller than the object. To do the mathematical analysis of this, to find the image distance, the 1 over di equals 1 over f minus 1 over do. And in this case, the numbers were given as the focal length was equal to -20, since it's a convex mirror that has a negative focal length. The height of the object, in this case, was given as 4 centimeters, and it says the distance of the object, it's placed 30 centimeters away from the mirror. So plugging these numbers in, we have 1 over -20, minus 1 over do, which is 30. Common denominator is 60, so we have -3 over 60 minus 2 over 60 is equal to -3 minus 2 is -5 over 60, and that can simplify to -1/12, which means that the di, the image distance, is -12 centimeters. And the negative on this means that the image is virtual. So that checks out with what we had earlier. For part C, we want to get the magnification, which is negative di over do. So that is -12 divided by the do, which was given as 30. That simplifies down to both the top and bottom are divisible by 6, so this simplifies down to a positive 2/5, which you can also write as a positive 0.4. So either one of these would be an acceptable answer for the magnification. The plus sign means that it is upright, so that part checks out, and then the numerical part is less than 1, meaning that it is smaller than the object, so that part also checks out. And then for part D, the height of the image is equal to the magnification times the height of the object, which is 0.4 times the height of the object was given as 4 centimeters. So 0.4 times 4 is 1.6 centimeters tall.